Good evening, everyone. Thanks for tuning in. Today, we'll talk about the online ML experiments and how do we run them at scale in Gojek. Quick intro from my side. I'm Roman Wozniak, lead product engineer from the data science platform team. I joined Gojek about 2 years ago, and since then, I've been working on the different components of Gojek machine learning platform. Here's the outline of what we'll cover today. So we'll start with describing a problem space, then move to how we approach the problem at Gojek. And then I'll provide a bit more details about the architecture and the features of our solution. And to close it up, I'll give you some ideas about our future plans for the development. So let's start with the problem space first, right? Hopefully, many of you are familiar with the ML development lifecycle. It usually starts with the data collection and the exploratory analysis stages, then progresses into the data cleansing and encoding or transformation before data scientists can train their first machine learning model. And after this, the model can be deployed and start serving traffic. But solving a business problem with machine learning is rarely a one-off task. So experimentation is just closing the loop and brings data scientists into the new iteration of modeling. Data scientists commonly include offline model evaluation steps as the part of the model training pipelines, but the offline model evaluation doesn't provide the comprehensive view on the model's performance in the real-world conditions. And here's the problem. Setting up online evaluation of the models is tricky because it requires the skill set and the familiarity with the tools, with the technical stack that is fairly different from what the data scientists are using for setting up the offline model evaluation. Hence, a lot of engineering support is required. Before we'll dig deeper into the problem, here's the basic terminology I'll be using during my talk. Let me just focus on the most important, what the experiment is. There is some amount of simplification in what I'll be saying, but in simple words, it's a way of routing traffic to multiple machine learning models in order to evaluate their performance. So the experiment is usually defined by multiple treatments and the configuration about the proportion of traffic each treatment should receive. And then each treatment is a set of configurations and rules describing on how to produce a response for the current request. To illustrate this, let's take a look on one use case or one problem that we've been solving at Gojek some time ago. I hope that many of you have used Gojek application together, right? So you might be familiar with the screenshot shared here. As a Gojek user, I usually don't want to type the address of my pickup location when I order the Go car ride. It's possible that I don't know the exact location. So if I'm at shopping mall or something, I probably don't know the address of this place. And also, it's possible that there are multiple pickup points or the drop-off points associated with the same address. So it potentially can cause the problem for the driver to find me and pick me up, right? So instead, I'd prefer to select my pickup location from one of the points available near my location. This problem can be solved purely from the engineering perspective, right? So it can be solved in a way that we can maintain some sort of the database that contains all of the pickup points with the geographical coordinates associated to each of the points. And then when a user is placing a new order, we can use some sort of geospatial index to fetch all of the points in the radius of, let's say, 10 meters or 20 meters or 50 meters from user's location and show them sorted by Euclidean distance. But the problem is that in crowded places, there could be many pickup points in the close proximity to a user's location. So the experience of making an order will still be suboptimal to the end user. And this is especially crucial in the situation when user is placing an order while being inside of a building where the GPS can't reliably pin user's location. So here's the question: can we improve this with ML model that ranks available pickup points not just by the distance between the points and the user's location, but also by taking into account some other features as the popularity score of the pickup points and also the historical, the past history of the given user's orders. So if in the past I placed an order from this pickup location, there is a high chance that maybe in the future I'll want to use the same pickup location again, right? And the experiment objective is to increase the proportion of orders that are made with a suggested pickup point selected. So if a user is constantly, if more users during placing an orders are selecting one of the pickup points suggested to them, it means that we are providing the relevant information for them, and they don't need to fall back into manually typing the address of the location. Of course, we don't want to roll out this ML-based approach to serve all of our users first without testing this on some smaller population of user. So we can set up something like A/B tests, where 90% of the traffic is still served with our existing ranking service, and only 10% of the traffic is routed to a newly trained and deployed ML ranker. This can be achieved with the load balancer in front of our rankers and a configuration that assigns corresponding weights to each of the rows. So can the problem be solved as easy as this? I don't think so. So there are a few of the issues why the simple solution will not work for most of the cases. First, it lacks the flexibility on how to define the traffic split criteria. You should agree that there is a difference between serving 10% of all the requests that are coming to some particular web service as opposite to serving all the requests from 10% of users that are using your web service. And the criteria for the traffic split criteria can be different for the different experimentation, and it's up to data scientists on what on how to pick up the experimentation unit for the given given experiment. And now, what happens if the data science team comes up with the idea for another ML model that they want to test? So they might be using other features for training this model, or they might employ the different approach for that model. So in this case, they'll have to reconfigure this load balancer to split the traffic between 3 different models, and also change the weights that assigns to each of the roads. So in total, there will be still 100% of the traffic distributed between three different roads. So some experiments can last only a few hours, and having so it probably will require some support from either engineering team or the DevOps team, right? And some of the experiments, they can last for quite short period of time in a matter of a couple of hours, and keeping the engineering team or ML ops team in the loop will set some constraints or some boundaries on the productivity of the data science team, and that's not something that we want to see in the organization. And then data scientists, they may want to restrict the experiment group by some other criteria. So probably there will be the cases where they don't want to use this new ML ranker outside of some geographic area. So maybe they want to have this experiment to be configured only to run in a particular city or a particular state. And such configuration is not naturally supported by the general purpose load balancers. And solution will have to either be inflexible, or it will require some engineering effort to handle this more sophisticated, advanced logic. And last thing is that the setting up experiment is just only the half of the deal. It also required to analyze the experiment results, and that's again not a trivial task, because it requires some data processing and the data collection pipelines to gather probably logs from the load balancer and persist them in some accessible format that later can be used by the data scientists. So again, engineering team in loop and the constraints on the data science productivity. So here's how we have solved this problem in Gojek with Turing. And what is Turing? Turing is our solution to the online testing and the evaluation of ML models. Turing is fast and supports low latency and high throughput traffic routing to an unlimited number of different ML models. It's extensible, so it's designed to support different type of experiments through the available extension points. It's scalable and cost efficient, and it automatically scales up and down based on the traffic volume. So it can support experiments at Gojek scale and simultaneously keep the infra bills under the control. And last but not least, it's completely self-serve and unlocks different data science teams to design and execute any experiments they want. Here's the high-level view on Turing's core components and the request processing flow. Now, let me cover these building blocks one by one, and we will start with Turing Router. So Turing Router is an intelligent routing service that orchestrates the rest of the system together. So it integrates with the optional pre- and post-processors and the experiment engine to retrieve the information about the treatment that should be applied to a given request. Data scientists, they can define what model should be the part of the experiment by specifying this model HTTP endpoints as routes in Turing Router. And in Gojek, our data scientists are using another product that is built by my team as well, called Merlin, for easily deploying machine learning models into the production and expose them through the network interface, such as HTTP endpoint. Moving forward, Enricher is an optional service that performs arbitrary transformation on the incoming request. Originally, it was designed to give the data scientists the flexibility to enrich the incoming request with some features from the external data sources. But it also can be just some arbitrary pre-processing logic written in the language of user choice. So data scientists should just pack it as the simple small microservice, package it in the form of the Docker image, and Turing will take care of all of the operational aspects of running it, such as deploying, scaling it, monitoring, and orchestrating together with the rest of the system. Next component is experiment engine. Experiment engine is responsible for managing experiment configuration and running them to generate a treatment for a given request. At Gojek, we use our proprietary experiment management system called Litmus for setting up the traffic split, randomization criteria, experiment unit for experiment, and treatment configuration. However, Turing was designed in the way to abstract out the experiment engine interfaces, and it can support other experiment engines as applicable modules. Now, ensembler is the component that encapsulates the logic on how to apply the treatment configuration to responses from ML models for computing the final response that is sent back to the calling system or client. So in a trivial case, there could be like one-to-one mapping between the treatment and the tested models. For instance, if the experiment engine responds with the name of a treatment that should be applied to a given request, such as, let's say, treatment A, in this case, the response from model A should be returned back to the client unaltered. But it's also possible that there are much more complicated ensembling logic. And that's why Turing also supports the dynamic model ensembling, where the final response could be the combination of responses from multiple models. In this case, the interaction between the data scientist and Turing is similar to how Enricher works. Data scientists can implement the custom ensembler interface as the microservice, pack it as a Docker image, and then Turing will take care of operational aspects of it. And the last component is the logs collector, which is responsible for capturing request and response data together with the treatment configuration and pushing this data either to Kafka streams or a BigQuery table. So this data is available for data scientists for further analysis and also training the newer version of ML models. And here's how the execution flow looks in Dynamics. So first, the incoming request from the client is sent to the pre-processing stage to enrich the request with features. Then the router parses the request to extract the experiment unit and the attributes of this experiment unit, and passes this data to the experiment engine to determine the treatment. So to give you an example, the experiment unit can be stored either in the HTTP header or in some field inside of the request payload. So Turing parses this data based on the provided configuration, extract this data, and send it to external experiment engine for running the experiment and retrieving the treatment configuration that will be applied to a given request. Simultaneously with sending the data to experiment engine, the pre-processed request is forwarded to all of the models that are part of this experiment deployment for model serving. And then responses from models are collected and sent to the post-processor, where they are ensembled together by applying the retrieved treatment configuration to all of the responses from ML models and sending them back to the client side. And finally, this response is sent back to the client, and logs collector writes the request response data to the logs sink, which is, as I mentioned, either the Kafka stream or a BigQuery table. And later, the last step, which happens already outside of Turing router, so later client can log the outcome data into the logs collector, where this outcome data is joined with the request response data that is logged at the previous step, based on some unique tracking ID associated with every request that is processed by Turing. So that's the end of the request processing flow and basically the experiment execution. So what else can Turing do? Before that, let's take a look on what powers Turing under the hood. So Turing taps on the great scalability of Kubernetes and some other open source components, such as Istio and Knative. And the data scientists interact primarily with the UI, Turing UI or Turing console. And the Turing console calls the Turing API. So Turing API is a controller with a set of the deployment management APIs that translates user-provided router configurations into a set of the Kubernetes resources orchestrated together. So Turing also supports multi-tenancy through the Kubernetes namespaces and the role-based access control rules. So the router or experiment deployment of one data science team is not affecting the deployments of other data science team because they are isolated. And each Turing router is a separate multi-replica deployment that scales up and down within the user-provided limit. It means that during peak hours, more replicas will be automatically added to handle a larger traffic volume. But during the off-peak hours, for instance, during the nighttime, the redundant replicas will be decommissioned to optimize the cluster resources utilization and ultimately to reduce the cost that we are paying for our infrastructure. Also, Turing supports more complex traffic rules to route the traffic to only a subset of model endpoints. This comes in handy when data scientists want to run experiments that span across different geographies, where the different versions of a model should serve the traffic from different areas. In this case, data scientists, they can specify some conditions, and only if the conditions are met, then the specific model will be activated as the part of this request processing flow. Also, data scientists can make changes to the existing deployments, and Turing will use the blue-green approach to make sure that the updated configuration can be safely deployed before switching to the traffic to the router with the updated configuration. And each change to the configuration is captured as a separate version of the deployment, and users can roll back or roll forward between these versions as they need. And of course, Turing provides a detailed monitoring dashboard to the users out of the box. So data scientists can also set up the threshold-based alerts on the key metrics, such as the response latency, throughput, and the error rates, and receive a notification in Slack if their alert contract is breached. And Turing also demystifies the deployment process by updating scientists with the deployment events timeline, and it makes it easy to debug any potential issues within the user-defined components, such as NVIDIA or Ensembler, by exposing container log through Turing console. But having all of these features doesn't mean that we can make Turing even better. So there are a few broad directions we explore to expand Turing's capabilities. Testing of ML models goes beyond online experiments, because some of the use cases, such as presented by Kilian Gobstopper, they are offline by nature, meaning that the model inference is not initiated by the client's request, but is rather triggered based on some recurring schedule or data availability. So for such scenarios, we are working on a standard way of executing batch experiments in Turing. And also, we want to improve the process of experiment result analysis by embedding the outcome metrics visualization into Turing itself. And last, in some scenarios, A/B tests, they are less effective due to the closed network effects. So we want to add into Turing support of other type of experiments, such as the switchback experiments and the contextual bandits. And here's how you can help us to do all of this and even more. We have multiple roles open in the data science platform team, and we are building the next generation of machine learning platform. So if you are interested in working with our data scientists and get from them the better understanding of the difficult problems at scale, and if you want to build such a powerful and impactful tools as Turing, please go and explore open roles and contact me directly or reach out to Gojek recruiters. And a few more reasons to motivate the right person to do so. The first one is that we believe in open source, and we happily contribute our work for the benefit of the data science community. We also use the cutting-edge technologies in our day-to-day work, and we have the full ownership of our products. And the last one, that's my favorite one, is that the data science platform team is set like a small startup company within a larger organization. So that gives us an extra flexibility on how we operate. And did I mention that Turing is open source? So now I did. Please follow the link or use the QR code for easier navigation and get more technical details about the architecture and the concepts of Turing. Or maybe you will even start contributing to the code base. And that's all I have for you today. Thanks a lot for your attention, and I'll be happy to answer any questions if you have some. Thanks.
All right, awesome stuff, Roman. Thank you very much. So yeah, so Turing and Berlin as well, they are both open source, yeah?
Yep, that's true.
Okay, so actually, so myself, I have been, so I guess before we bring in additional questions from the audience, perhaps, because I myself explore many different model serving, open source tools. There's Selden Core, there's Bento ML. These have been garnering popularity recently. But are there distinct motivations behind, why do you guys actually develop your own set of tools?
Oh, that's a very good question. So our journey to start building the different products that are orchestrated into a single ML platform started probably at around the beginning of 2019, I guess. So it's almost 2 years ago. And at that time, we didn't have any solution for the model serving. That was, the data science team at that time, they've been using some ad hoc approaches to serve the traffic with the models. So we started doing the exploring and doing some spikes around the available tools at that time. We tried to use Selden at that moment of time. It didn't provide us with the satisfactory results for the latency of the request processing. We basically delivered the prototype with Seldon, and then we realized that for some of the use cases, the latency constraints or the latency requirements for our use cases is as low as like 10 milliseconds for the entire request processing workflow. And after the intensive benchmarking and load testing of Seldon at that moment of time 2 years ago, we didn't manage to get to that point. So that's how we started exploring the other tools and building the easier to use abstraction on top of this.
By Shengong, why not have a beta group and allow the users who are open to use it to opt into using the other service?
So probably the person is asking why we are just not testing those experimental features or experimental approaches on the beta version of the application, where the users can voluntarily sign up for this beta process. The use cases for ML experimentation, they are not limited only to something that is kind of directly affecting or directly visible to the user. So there are many approaches that are deep inside of the Gojek infrastructure. So it's not always observable or easy to observe for the end user. And that's why it's basically, I mean, it's kind of, there are no tight connection between the application or a version application or the beta version of application and a stable version of application versus the entire number of ML experiments that are running under the hood inside of Gojek. So just to maybe clarify this, the example that is used here, such as this one with the pickup points, it's just very easily being mapped to this scenario when the user might volunteer to try this new experience and to be suggested the pickup points. But for some other use cases, so ML models can decide on how to allocate the driver that will be giving you a ride. And there are many other use cases that is not that straightforward to ask user to either opt in or opt out from.